Okay, so this is the take-home questions. And I'm gonna go over this problem here. Again, very few of you got this problem. I gave you a lot of partial credit though. Okay, basically, I wanted you to make this from these precursors. So you got to figure out which ones you needed to use. Then you needed to show the reactions of the precursors to get to the final ester. Okay, so this ester has got a 2-carbon alcohol and a 1, 2, 3, 4, 5, 6 carbon acid. So whenever you make an ester, the backbone number of carbons does not change. So we need to find something with 2 carbons and 6 carbons. So we're going to take those 2 precursors, make them one, this goes to the acid, and this would go towards the alcohol. All the others, the carbon numbers don't match. Does that make sense? Okay, so how do we turn this into an acid? Well, what we can do is if we add water across the double bond, we'll get an alcohol. We'll get a mixture, but we'll get an alcohol. Okay, so we're going to take this alcohol here and we're going to oxidize it. Oxidized primary alcohols go first to an aldehyde, then to an acid. So 2 oxidation steps. Okay, so now we have the acid. We're going to do the same thing with that. We're going to add water. Then we're going to oxidize it. No, excuse me, we're already there. So now we have an acid. And the alcohol. Okay, so that's what I wanted to see. Now, I don't know if my directions were unclear or what. A lot of people didn't even look at the suggested starting point. They just told me how to make it. Well, I wanted you to start with those molecules on the left.
For me, I think it's because I've never seen it. So,
You didn't see this.
well, actually, I did. I just looked at it. I just didn't know we have to turn it in on campus. Because I have it on my test that I gave to. It's stapled on there. I just didn't know we had to turn it in. That was the other thing.
No, so we sent it to your test?
Yeah.
Well, that's what I want.
Oh, okay, but
The beginning of the take home, it says bring this.
yeah, I stapled it and. But you're saying to turn it in. Sorry. Oh, okay. Oh, I was confused.
Well, normally on You didn't check your email. That's something you should do.
Yeah.
Okay, so any questions about that problem? Okay. And the rest of these were pretty standard. Now, one of the issues were these two. Those are from unit 2. They're this is a Hemi Keytal, and this is a Keytal. I wanted to know how you made them. Just remember, there's no final in this class because every test is cumulative. Um, I mean, these are really standard. We shouldn't have any problem with these if you studied. Okay. All right, so I'm gonna look at test 4 practice tests. Are there any more questions about the take home? Okay, and I will allow test corrections like before. If you got a C or D, you can do corrections. All right. Let's name these. Okay, it's an amide, and it's got 2 methyl groups coming out of that nitrogen. Okay, so we've got, actually, it's not an amide. It's just an amine. So it's got a 9-carbon backbone. So that means it's going to be a nonane. And it's got an amino group on carbon number 2. Okay, so we're going to name it as basically a branch off of the backbone, an alkane backbone. Similar to this one, this is got a aniline backbone. So this structure here, that's aniline. And we've got 2 ethyl groups coming off of that nitrogen. So it's N-diethyl aniline. Okay, so we've got an amide. And that means we're going to have the amide now has got no nitrogens I mean, it has no groups coming off the nitrogen, so it's just a plain NH2. Then we have 1, 2, 3 methyl group and 3, 4, 5, 6 ethyl. Now, if we had some groups coming off that nitrogen, we had to have ends there to distinguish which ones were coming off of the nitrogen. Otherwise, assume it's NH2. Okay, so we've got ammonium chloride. Now, ammonium is a quaternary amine group. That means it has four now off that nitrogen. So chloride is -1. And then this is going to be +1. And the nitrogen's got an ethyl and a methyl group coming off of it. And then it's got a propyl group coming off of it as well.
Or three.
Hmm?
Three. No.
Well, it's the propyl backbone. And it's amino branch. An amino part coming off the nitrogen are 2 methyl.
I can understand that that's all of them. Problems, but I don't.
The that's the backbone. It's a 3-carbon backbone. So it's just like
We do it like that.
hmm?
Bottom.
Yeah. Oh, sorry. And then it'd be like. So that orientation makes more sense. Okay, we have aniline again. And 1, 2, 3 propyl group. Okay, so this is an amide. So the nitrogen has got 2 methyl groups coming off of it. And this is 5 carbons long. Now carbon number 2, we have a phenyl branch. And you can also have the 3x5 card for next week's tests, both sides, just like all the other tests.
Is the textbook?
Wednesday, yeah. I'm gonna review again on Monday. Okay, this is just gonna be a okay, so one of them is gonna be leucine on the left. On the right will be phenylalanine. Structure number one. Structure number two is going to be phenyl. Not a dipeptide. It's a it is a dipeptide. It's got two amino acids in it, but one amide bond or one peptide bond. Okay, so that's basically what you do. Because in a test tube, there's no way to determine which one comes first. In the body, an enzyme will determine which comes first and which comes second. And there's a long process by which proteins are made, similar to the way DNA is constructed in your body. Okay, there's something that I will read off what the required sequence is for the amino acid. That's assuming you're doing a neoprotein genesis. Otherwise, you're going to input the protein, like for meat or for vegetable protein. Okay, 3-aminopentane. Okay, so there's no NN, so there's nothing coming off the nitrogen. So it's just going to be hydrogens. And it's a five carbon backbone. Name two common biological molecules that are amides. Name any protein. Anything shorter than a protein is also, like insulin is a polypeptide. Could have named that. Any of those that have amides or peptide bonds in it. And there's lots of them. You don't have to draw the structure, you just have to name it. You could name globular protein, fibrous protein. I mean, any of those work fine. Okay, looking at intermolecular forces. This question keeps coming up on every test. Okay, so we have okay, they all have London dispersion forces. So this one has only LDFs. This one has hydrogen bonding, dipole, and LDF. This one has dipole, and this one has hydrogen bonding, dipole, and LDF. Okay, now these two look equivalent, but they're not. The acid has a stronger hydrogen bond than the amine. So this is going to be number 1. Number 2 is going to be this one. Actually, this is, I thought they were the same thing. Let me rank the problem 10, and then we'll look at that problem 11 here. Okay, so this is going to be number 1. Number 2 is going to be this guy. 3 is this one. 4 is this. Now this one has octanol in there as well. So okay, so they all have LDF. This is LDF only. This has got hydrogen bonding. Dipole, dipole. This is dipole. Okay, so we have 3 hydrogen bonds here. Okay, the strongest one is this one here. This comes second. This would be third, and then 4 and 5. So the acid is by far the strongest hydrogen bonding. Right under that's going to be the alcohol. And then the hydrogen bonding with the nitrogen, again, is not as strong as with the alcohol or acids, so it's third. And then the aldehyde has no hydrogen bonding, only dipole-dipole. Okay. Most soluble in water. Water is very polar. So which is more polar between these two? Okay, so this would be most, least. This has hydrogen bonding, dipole, dipole. This has hydrogen bonding and LDF. So. But again, we have the nitrogen hydrogen bonding is not as strong as the OH alcohol hydrogen bonding. So that's why the hexanol will be most soluble. The hexamine is going to be least soluble, still going to be soluble though. Because it does have that hydrogen bonding. And then they want to draw the structures. And it doesn't say, let's call that this. Let's call that this. Okay. Usually when you don't specify, it's carbon number 1. Okay, so we have acetic acid. And we have a pH, an alkaline pH. So that pH is greater than 7. So that means there's going to be OHs around to grab hold of that proton. And then we have trimethylamine. So this is going to be ionic. Now, if the pH is less than 7, this would be no reaction. So let's do the same thing when we change this to pH 1. So this proton is going to attach to that electron pair. So I always have this question on there. The difference between this one and another one might be the pH value. Okay, reactions. Okay, if you throw an amine in water, what's going to happen is the H on the water is going to attach there. So you're going to end up with this is called ammonia water. So here we have an acid chloride. Means we can make an amide out of this. So let's name these. So this is going to be methylamine. And it's the same one down here. This is going to be the benzyl chloride. And this is going to be benzamide. So two ways to make this guy. Okay, it's an amide. That means it's going to require some form of an acid and an amine. So the amine is going to be Um, that. And then this here is we're first going to do it with the acid chloride. So it's going to be a 1, 2, 3, 4. Methyl butyl chloride plus dimethyl amine. And this guy here is going to be the reason why I erased the A, you had two A's together. Whenever you have two vowels together, you drop one of them. Okay, okay, that's using the acid chloride. Now we're going to do the anhydride. So this is going to be 3 di-3-methyl butyl anhydride. Just gonna look like this. And we're not using the acid because that reaction's too slow to even be called a reaction. So it's not included. Unlike the ester, which it's slow, but it's fast enough to be included. Okay, what's an enzyme moderator? Two kinds. Okay, well, there's an inhibitor and a mental block for the second one. It it speeds up the reaction, but there's a name for it though. Well, it is, the whole enzyme is acting like a catalyst. No, but there's another, this is, um, two kinds of moderators. One slows it down, one speeds it up. Um, It'll come to me in a minute. Okay, that one speeds it up. Okay, so let's draw kind of like what I had in the presentation. So we had, here's the substrate. And it's going to fit in here. And then down here, okay, so this is the active site here. And this is going to be the allosteric moderator. Okay, so what happens when things get inhibited is when this attaches. Let's okay, so when it inhibits, the shape of the active site changes. So instead of looking like this, it's going to be different. So let's change it. So it will no longer fit. Okay, now if it speeds up the reaction, normally what happens is it makes the active site uh, exist so the substrate can fit in there. So one time, to slow the reaction down, to inhibit it, the active site is changed, so the substrate doesn't fit in there anymore. When it speeds it up, the active site, without the moderator, doesn't fit. And as soon as the moderator attaches, then the active site is available for the substrate. And this is called allosteric modulation. So there's two active sites on most enzymes, one for the moderator and one for the substrate, most of the time. So this is one way that biological systems can control enzymatic reactions. Okay, so amino acids are not named as acids because physiological physiological pH is slightly alkaline. Means that there's no proton, the proton is already gone. So it exists as the acid salt. So instead of glutamic acid, it's glutamate. So that's the acid salt, glutamate. And this is the acid. Now in your stomach, the amino acids are all named acids because that's an acidic environment. Outside the stomach, it's all slightly alkaline, so everything is in the salt version. Okay. So it says, what does an enzyme do in your body, including a discussion activation energy diagram? Okay, that was the one that we had like this. We had potential energy here, and then we had substrate. Product. Then we had a activation energy that broke apart the substrate into pieces that come back together to form a product. Now, without the enzyme, let me. Okay, so the activation, and this is called the okay, that hump is the activation energy. That's the energy required to break apart the reactants or break apart the substrate. And that determines how fast the reaction goes. If the activation energy is very high, the reaction's slow. Like I gave you the example of charcoal and diamonds. Diamonds convert to charcoal, but very, very slowly, because charcoal is more stable than diamonds. Okay, so that's where I was looking for this. Okay. Here are the crosslinks in a typical protein. And I want you to pick the one that's most and the one that's least. Okay, so this is strongest, and it's the reason why it's covalent. Covalent bonds are stronger than ionic bonds. This is ionic, so it's strong, but not as strong as the covalent one. So this would be ionic IMF. This is number 3, and this has got H bonding. And this is number 4, LDF only. So that's why that cysteine amino acid is so important, because once it makes a cross-link, it's very strong to undo it. So when you get a perm with your hair, this is why it's so stinky, because your hair has to go into a solution where it breaks that breaks that sulfur-sulfur bond. And then you do your hair, you straighten it or curl it, and then you reestablish the sulfur-sulfur covalent bond. So there's always 2 steps to a perm. Oxidation step and then a reduction step. I think that's it. Yes. Okay. So this unit's got a smattering of everything. It still bugs me, that term for allosteric. Okay, so that's what I wanted to cover today. Practice test And I wanted to go over that one take-home problem. So those of you who did not do the take-home test, possibly not being here right now, will not know that you can do the makeup for the take-home tests on those take-home problems. So the advantage of coming to lecture in person rather than listening to the video is one of the advantages. All right.